Good morning, everyone, and welcome to quarantine day 2 this week. I wanted to start off with just kind of taking a look at some of the questions that were on that checkpoint that everyone started on Friday, except for Alexis, who wasn't able to be with us because she was, talking with robots or something. But not everyone got finished up. And I figured that we kind of, since a checkpoint is meant to just kind of gauge your understanding and it's not meant to be like a big serious grade, that we'd go over it while it's still fairly fresh in our heads, and that maybe I could work some of these by request uh, for you. So I know it's been a few days since you've seen this, so what I'm going to do is I'm just going to show this one page at a time here. And if there's a problem on there that you would like for me to work, then if you'll just type the problem number in the chat, then I'll be happy to work it for you. If not, then I'll, let 30 seconds of silence go by, and then I'll move on. Actually, I think you might have a button well, I don't know what buttons you've got in your chat there as far as showing your status, but um, if you want me to go ahead and move on, then you can just give me a thumbs down, and that'll tell me that I can go on from this page and go take a look at another page. But take a look at problems 1, 2, and 3 right there, and if you would like for me to show you how to work those, or you can work along with me, then just shoot me a number in the chat window. Drinking the coffee. All right, I've got a vote for number 1. So I'll go ahead and let's look at number 1. And if you want to put in another vote while I'm talking, that's fine. Or, you can work number 1 along with us here. So number 1 says, late traveler rushes to catch a plane, pulling a suitcase with a force directed 30 degrees above the horizontal. If the horizontal component of the force on the suitcase is 60.6 newtons, what's the magnitude of the force exerted on the handle? Fantastic. Let me get some paper. Here we go. So let me start by making a diagram of this. So here's our suitcase, and he is pulling it at an angle of 30 degrees above the horizontal, correct? So the horizontal component of the force is 60.6 newtons. That means if we take this and just look at the x portion of that force, the x portion of that force is 60.6. They want us to find the actual force vector right here. Okay, yeah, no, that's fine. Most people forgot to grab their binders and checkpoints, so don't worry about it. Just take a look at what you can see in the thing here. We'll go through page by page, and if you see one you're like, oh, hey, I hate that problem, work that one. That's fine, okay? And again, you can work on my paper along with me. I think it's good practice. I am videoing this, and so you can always, pull the video back up and torture yourself later. So what I want to find is I want to find what's the magnitude of the force exerted on the handle. So I'm looking for the hypotenuse of this right triangle. So this first one is just going to be a classic SOHCAHTOA. So I've got adjacent and hypotenuse. So I'm going to be using cosine. So in other words, cosine of 30 equals 60.6 over h. Now there's awkwardness there, and so however you solve it from this point, that's up to you. I like to invert things, you know that. So I'm going to do 1 over cosine of 30 is equal to 60 point, I'm sorry, nope, hypotenuse over 60.6. So then I'm going to do 60.6 divided by cosine of 30, and it should give me what I need. So calculator, cosine of 30. So I get an answer of 69.97. Going back up to my answers, that's closest to 70 newtons, and so I'm going to go with B there. Okay, so that's problem 1. Anyone would like me to show you 2 or 3, or talk about 2 or 3 before we move on? Just shout it out in the chat. 3, please. Excellent. As a basketball player starts to jump for a rebound, the player begins to move upward faster and faster until his shoes leave the floor. At the moment the player begins to jump, the force of the floor on the shoes is blank. Now this was a hashtag question, and this is really good when we're talking about, let me move the camera up a little bit here. It won't let me move the camera up, I'll move the paper up. When we're talking about forces and force diagrams and stuff. So if we've got our player here, okay, so the force of the floor on the shoes. So in order for him to jump, he imparts a downward force to the floor, okay? Now the floor is going to impart an upward force equal to his downward force. That's because of Newton's third law, which I know we just kind of dipped our toes into when you guys did that lab, so if you don't totally get this, that's fine. We are going to talk more about it this week. And so it's this upward force from the floor that's actually pushing him up off the floor. Now before that happens, the other forces that are acting on him are the force of gravity, okay? Normal force is acting up. And so when we're talking about the force of gravity, it's pulling on his mass, right? And so when we talk about someone's weight, because all of these answers have to do with weight, we're really talking about the measure of gravity's attraction on his mass. Okay, the greater your weight, it means that you've got greater mass because there's greater attractive force between you and the planet. So in order for this box, which is our player, to end up going this way, that means the sum of all of the upward forces has to be greater than the sum of all the downward forces. Now, kind of touching on some questions I saw from your reading yesterday, that means that the sum, or the sigma, or the net force has to be in an upward direction. So that means that that would be the normal force, and that would also be this force that the floor is pushing up on. Now, in order for that to overcome and get him off the ground, that means that this force that it's pushing with has to be greater than the force of gravity pulling him down. Force of gravity pulling him down is directly related to weight. Therefore, the force of the floor on the shoes is greater than his weight. I know that's an awful lot of words for such a, make it short and sweet answer, but that's what's going on. And it all has to do, with the fact that you don't get acceleration unless you have an unbalanced force, unless you have a net force that is more than zero, or less than zero if you're talking about the negative direction. So if that doesn't totally make sense, that's fine. We're going to look at it some more this week. Nobody has said anything about problem 2. So I'm going to assume that you guys are good on problem 2. Problem 2 is a projectile motion question. Do we want to look at 2, or should I go to the next page? Yeah, we should probably look at 2. All right, that's fine. Track star in the long jump. Okay, There's another vote for 2. Track star goes into the jump at 12 meters per second, launches herself at a 20-degree angle above the horizontal. What's the magnitude of her horizontal displacement? Great. Okay. So what it's asking for here, if we can kind of get a picture of this, here she is. She is going to go in a parabolic flight path, split into 2 parts, the upward flight and the downward flight. She is launching herself at 20 degrees above the horizontal. And if we look at her starting vector, it is 12 meters per second. And so what we're looking for when we're looking for horizontal displacement is we are looking for her total delta x. Okay? So let's make a table of what we know and what we don't know. Let me move this deer out of the way. I don't know what that's about. So we don't yet know time. And I think what we're going to want to try and find, first of all, is going to be hang time for the upward portion of her flight. We also, well, we can figure out velocity of x by doing some SOHCAHTOA here, right? Because Vx is going to be this part of the triangle. So let's see, we've got adjacent hypotenuse, so we're going to use cosine. So cosine of 20 equals v of x over 12. So 12 times cosine 20, go ahead and slap that out real quick. I get 11.28 for my Vx. Just want to put that here on my table. So now what we're going to do is we're going to, well, we need to figure out VO. That's going to be the y part of our starting triangle. So then we're going to say sine of 20 is equal to our VO of y over 12. So 12 times sine of 20, I get 4.1. So for our y, VO equals 4.1. We already know, if we're just looking at the upward half of the flight, that at the top her VF is going to be 0. We know that her acceleration is negative 9.8. Actually, the problem wants us to use, negative 9.8. So now I think we've got enough information we can solve for hang time for the first half of our flight there. So on my big 5 chart, okay, if we don't know, or we're trying to find time, we don't know delta y, we don't know how high she's going to go. So looks like we're going to use big 5 number 2 to find t. So we can rewrite this one right here, Vf equals Vo plus At. And this is all for the y part, by the way. Vf equals Vo plus, that's not a plus, plus At. So rewriting this, we're going to have Vf minus Vo over A equals T. Y'all check my math. Does that make sense? Okay. If you see something I'm doing wrong, just yell at me in the chat. That's fine. So when I plug this in, I'm going to have Vf is 0 minus Vo. Vo is 4.1, so I'm going to have negative 4.1 over negative 9.8 is going to give me T. So I'll do, move that out of the way there. Where's my negative button? Negative 4.1 divided by negative 9.8. So my time is 0.418 seconds. Now that's just my time going up. So if I want to get my total time, I'm going to take that times 2. That'll give me my total flight time, which is 0.8367 seconds. Now I'll use big 5 number 1, where delta x, wait, is big 5 number 1? Okay, yeah, average velocity times time. So we know our total time is this 0.8367 seconds. We know our velocity for x is 11.28. So I'm just going to take that answer times 11.28. So this tells me that she's going to go a total of 9.44 meters. So let's look up at my answer choices. 9.44 meters is closest to this 9.2 meters. So I'm going to go with that for my answer. So that's the first page. We're 15 minutes in. Let me take a look at page 2 here. And y'all can tell me if there's any on page 2 you'd like to see. Okay, we've got problems 4, 5, and 6. Problem 4 is acting about a falling object. Problems 5 and 6 are dealing with this free body diagram on this car. So would you like to talk about any of those 3? Not very much math on any of those 3. Actually, no math on any of those 3. Okay, I got a vote for 4. Okay, some object falls toward Earth. Let's get rid of some choices that are ridiculous. Okay. So let's see. The object does not exert a force on Earth. Well, we already know that, if the Earth is exerting a force on the object, that's gravity, then third law says that the object has to be exerting an equal and opposite force the other way. So, in other words, what's happening here is that the Earth is falling toward the object, but the reason why it doesn't seem that way is because there's such a big difference in masses. So, it's not that Newton's third law does not apply. It's not that the object does not exert a force on the Earth. Now, either the object exerts a downward force on the Earth, which means the object is pulling the Earth down, which makes no sense, or we can say that the upward acceleration of the Earth, even though it exists, it's negligible because of Earth's ridiculously large mass. So, hey, there's another B. Again, we'll look at more Newton's law stuff this week. Does anyone want to talk about either 5 or 6? There was a trick to 5 and 6. Okay, 5 and 6. All right. So let's look at this free body diagram real quick before we talk about anything having to do with questions. So first of all, looking at the up and down here, is that a balanced or an unbalanced horse? It looks to me just at those 2 vectors that that's unbalanced because they're not the same. But if you look here, this arrow is going slightly up and to the left. So I'm going to go ahead and kind of assume that there is some balancing going on with the y portion of that arrow. That's not the important thing. Which of those 2 forces are due to gravity? The one going up or the one going down? So which of the following is a gravitational force acting on the car? Gravity, as far as I know, always pulls down, right? So this 14,700 is the gravitational force. So hey, there's another B. Now that one's easy. This one right here, it wants to know the 5,800 Newton force. It wants to know what does it represent. Now read the entire thing. It says it shows a car being pulled by a towing cable. If the car is being pulled, is it being pulled by the 5,800 Newton force or is it being pulled by the 775 Newton force? just looking at those forces, which one is stronger? This guy right here, right? And so we have to assume that that 5,800 newtons is the force exerted by the towing cable on the car. Because otherwise, the car wouldn't be getting pulled. The car would be pulling the tow truck. The tow truck's actually over here off to the left. Okay? That's what was kind of tricky about that. If you didn't really take a look at those numbers, you might have assumed that the tow truck was here on the right. Okay? The car is being pulled backward. And that's that page. Stop me if I'm going too fast. Page 3 is our last 4 problems. We've got problem 7 where Christian's rolling a rubber band ball off a desk, and we want to know how fast it was going. That's a lot like that lab you guys did. Oh, there's a vote for 7 right off the bat, so we'll look at that one. Okay. Let's look at 7, then we'll talk about the other ones. Get some fresh paper here. So just like the lab y'all did, Christian rolls a rubber band ball off the desk. If the desk is 0.9 meters tall and the ball lands 0.5 meters away, what was the horizontal velocity of the rubber band ball as it went off the table? Okay, so let me start by drawing a picture. Okay, here's my table. Ball is going to follow a parabolic flight path and smack the floor. It says it's going to smack the floor 0.5 meters away. So that 0.5 meters is going to be my delta x. The desk is 0.9 meters tall. So this 0.9 meters right here is my delta y. Okay. It wants to know what was my v of x. So in order to solve this, I've got to know what my flight time was. Once I know my flight time, it'll be easy to see in that amount of time, if it only went this distance, then I can figure out the velocity by using 7, 8, 9, 10. Thank you. Yeah, okay, fine. We'll look at as many as we can until we run out of time. We need to figure out time so we can backtrack and figure out how fast it was going when it left the table. So, since we know how far it's falling here, then we can make the y portion of our table. We know that for our y, VO is 0 because it hasn't started falling yet. We don't know VF yet. Acceleration is going to be 9.8. And so okay, and we also know delta y is equal to 0.9. So let's look at our Big 5 chart and figure out what we can use to find time. We don't have VF, so I think we're going to use Big 5 number 3 rewritten to get rid of the VOT part and then to get T by itself. So if I recall correctly, that means that T is going to equal the great big square root of, let's see, 2 times delta y over A. I think that's the one that we ended up using when you rewrite that. So plugging in what I have right here. So 2 times 0.9 would be 1.8 divided by my acceleration, which is 9.8. So let's pull that up. Square root of 1.8 divided by 9.8, close parentheses. So I get 0.4285 is going to be my time. Okay. So actually, why don't they turn the stupid bells off? I'm like the only person in the building. This is my personal hell, folks. So, I hope you're enjoying your nice, cozy, bedrooms and your jammies. Anyway, so that's going to be our time. So let's look at Big 5 number 1. Big 5 number 1 says that delta x equals v times t. So if I've got t and I've got delta x, I can take delta x divided by t to get velocity. So our delta x we already said was 0.5. So I'm going to do 0.5 divided by my answer. My velocity here is 1.16 or 1.17 meters per second. And it looks like A is my best choice. So we got to one that's not B. Okay, so we're getting more votes for 8, 9, and 10. Let's look at 9 and 10 first because there's no math here. We'll go back and we'll look at 8. Okay, so according to Newton's second law, when the same force is applied to two objects of different masses, now you kind of dipped your toes in this with the lab that you did. When you have your two carts and you put a mass on the two carts and they push off each other, they're pushing off each other, and so they're both getting the same force. But when there's a greater mass, the heavier cart experiences less acceleration, right? So Newton's second law is actually force equals mass times acceleration. So in other words, if I take force divided by mass, that gives me acceleration. So let's go through here and get rid of answers that don't make sense. The object with greater mass will experience a great acceleration. The object with less mass will experience an even greater acceleration. That's a iffy statement. B, the object with greater mass will experience a small acceleration. The object with less mass will experience an even smaller acceleration. Definitely not. Because the one that's smaller mass will have more acceleration. Object with greater mass will experience a smaller acceleration. Object with less mass will experience a greater acceleration. I'm really liking him. And D, the object with greater mass will experience greater. Now that's exactly opposite. So between A and C, I really like C better. You could argue that A is sort of saying the same thing, but I don't like how it's saying it. C makes a lot more sense. 10, I think I mentioned this earlier. If a non-zero net force is acting on an object, then the object is definitely blank. In fact, I think we talked about this one in class. So here's an object. There's a non-zero net force acting on it. This force vector is greater than this one. And so when you've got a non-zero net force, that means you've got acceleration happening. It might be speeding up, it might be slowing down, but it's definitely not staying at a constant velocity anymore because those forces are not balanced. So we'll come back up to number 8. Another projectile motion problem. This one's not too bad. Mr. King's in a private northwest tower at his evil lair. On a whimsy, Mr. King fires a cannonball horizontally from a cannon at the velocity of 147 meters per second. Neglecting air resistance, where will the cannonball be 4 seconds later? Okay, so here is tower, right? Here's where cannonball is starting. Cannonball is flying parabolic path. Now, it says, where will it be 4 seconds later? As far as downrange, what we're looking for is we're looking for delta x. Now we know time. Time is equal to 4. We know velocity of x. Velocity of x is 147. So using big 5 number 1, which says that delta x is equal to velocity times time, I'm going to go 147 times 4. Which is just 588. So 588 meters downrange, right on the dot there. That one, that you were expecting it to be harder, and it really wasn't. Really, if you had to pick one problem on this entire thing that required the most work, that's probably problem 2 back over on the front page, because it was full-on projectile motion. Everything else was just bits and pieces of that. So before I set the checkpoint aside, does anybody have any other questions? And I'm fine if you would like to unmute yourself, or you can just type it in the chat. Gage is still with us. You really have to admire his determination. Hope he's enjoying this. Okay, so everyone is remaining silent at me. So we've gone 30 minutes, and that's quite a bit of talking about physics. I had in my head to also take a look at some more of these practice problems. I'll just go ahead and spoil it for you. Tomorrow, your assignment is going to be working on a few more of these practice problems. I'll upload another copy of this. I know we've done some in class, like we've done 1, 2, 3, and 4, or maybe we didn't get all the way through 4. I know a lot of you don't have this with you, so I'll figure out some way of uploading and rescanning this, and then I think we'll just wait till tomorrow's Zoom. I'll work a few more of these, and if you can tune in live, that's great. If not, then you'll just need to watch the video and work a few more along with us, and then your homework will be whichever ones we don't get to by the time that class is over tomorrow. So I'm going to go ahead and I'm going to stop the recording now.